So let's see about the tangential and normal components of acceleration. There's an object moving along the path given by r of t. Somewhere along that path, anywhere on that path in fact, the velocity vector points in the direction of motion. The acceleration vector always points towards the inside of the curve. Now the acceleration vector can be broken down into its component pieces, and that's what we want to talk about in this section. There is a component that is in the same direction as velocity, and then there is a component that is orthogonal or perpendicular to that. Now if we take a look at the unit tangent vector, abbreviated capital T, it points in the same direction as the velocity vector, but it is 1 unit long. And the unit normal vector is perpendicular to that. Now we're interested in actually what's called the principal unit normal vector, which is the one that is pointing towards the inside of the curve. Now the component that's in the direction of the unit tangent vector is actually the projection of the acceleration vector onto the unit tangent vector. By definition, the projection of A onto t is the dot product of A and t divided by the magnitude of t squared. Well, since the magnitude of t is 1, that's just A dot t. And the component that we call the normal component is the projection of the acceleration vector onto the normal vector. And so the projection of A onto n would be the dot product of A and n divided by the magnitude of n squared, and the magnitude of n is 1, so that's just A dot n. So these are the tangential and normal components of acceleration. However, they're not very easy to compute from these formulas, so we'll look at alternate forms. So we want to come up with different forms for A sub t and A sub n, the tangential and normal components of acceleration. Now, the definition of the unit tangent vector is that it's the derivative of r divided by the magnitude of the derivative of r. We're going to use, however, the same thing in terms of v's. We're going to solve for v in the definition of the unit tangent vector, and then we're going to do the derivative of that to find the acceleration. So by the product rule, we would have the derivative of the magnitude of v times the unit tangent vector plus the magnitude of v times the derivative of the unit tangent vector. And it's a lot of work too, so we're going to simplify this some more. We'll multiply top and bottom of the right-hand term by this quantity, basically so that we can rewrite this portion as t prime over the magnitude of t prime. Well, t prime over the magnitude of t prime is the definition of the unit normal vector, so we can replace that with just the n. So this is also another form of the tangential and normal components. The coefficient, or the thing multiplied by the unit tangent vector, is the tangential component, and the thing multiplied by the unit normal vector is the normal component. So that's where they get their names. We're going to do some manipulating on this. In this formula, we've got this quantity here, the derivative of the magnitude of v. That is not a nice thing to deal with. Let's do a little work on that. So we're going to do the dot product of v and a, and remember that the definition of the unit tangent vector is v divided by the magnitude of v. That allows us to write v as the magnitude of v times the unit tangent vector. So we'll do that, and then we'll use the properties of the dot product. And our dot product, we're going to use the properties of the dot product, the associative property. See our two t's. See the t's and the n's. Associative property, distributive property used on this would give us this. And then we'll use the properties again. And again, notice here we can do these. And we come up with these quantities. Now, first off, the t dotted with t. Unit tangent vector dotted with itself is a 1, and the t dot n, any vector dotted with a vector perpendicular to it, is going to be a 0. So we can totally eliminate all of this second term since t dot n is a 0, and we end up with this. Now you can see from there we can solve that for the magnitude of v's derivative. So solving that for the derivative of the magnitude of v, this is what we end up with. And so that quantity is a little easier to deal with, and that's the tangential component of acceleration. And now we want to do some work on our normal component of acceleration. And let's see what we can do with that. First thing we're going to do, remember the definition of curvature. We're going to use the definition of curvature to rewrite the magnitude of t prime as curvature times the magnitude of v. And so we'll just replace the magnitude of t prime with the curvature times the magnitude of v. Now that's magnitude of v, and the other magnitude of v is going to give us the magnitude of v squared. And so the acceleration component that we call the normal component could be written as the curvature times the magnitude of v squared. We're going to work a little bit more on that normal component of acceleration by taking the acceleration that we found earlier and the velocity in this form and doing their cross product. Using the properties of the cross product, we're going to rewrite and use properties again. Here's our cross product that we're going to rewrite using the properties. And so look at this, the t cross t, we've done that before, is the 0 vector. So that's going to eliminate this entire term, and we're going to end up with just this. We're going to take that. Now t and t prime are orthogonal, so the t cross t prime that we see here is the magnitude of t times the magnitude of t prime times the sine of 90 degrees, orthogonal. Okay, the sine of 90 degrees is 1, the magnitude of t is 1, and so we end up with just the magnitude of t prime, and we can replace that t cross t prime with just the magnitude of t prime. And then solve that for the magnitude of t prime. Now, in the definition of curvature then, we can replace the magnitude of the t prime with the magnitude of t prime that we just found. And so we end up with this expression for curvature, which simplifies to this. So we'll put that back into our acceleration function and then simplify that. So we end up with another version of the normal component of acceleration. So we end up with all of these versions of the tangential and normal components, and those are the ones that I've got in blue and red, the most useful of which is this one. Most of the times in what we'll be doing, we'll be given the r, the position function. Well, the v and the a are just first and second derivatives of that. So you can see in this formula, the only thing we have to deal with are combinations of the first and second derivatives of r. No curvatures, no tangent vectors, no normal vectors, just derivatives of r. And we're going to work through this example to see how to find the tangential and normal components. And of course we will use this version of the formulas. So we need to find v and a. So to find v, we just do the derivative. To find a, we do the derivative of that. And then we find the tangential component, which is the blue, by doing the dot product. We can pretty much do that in our head. And then the magnitude of v. So there's the dot product. There's the magnitude of v. And then some simplifying. Likewise, we can find the normal component by using the red part. Of course, v cross a can be a pain to do by hand. We can do it on our calculator, or we can go take time to do it by hand, but I'm not going to put all that on the screen. You should know how to do v cross a. Magnitude of v is the same thing we just found, so we can recycle the radical that we found in the first part. We just need to do the magnitude of v cross a. We can almost do that one in our head. Of course, we have the other option of programming the two formulas into our calculator. So here in the first one, which I've called T comp for tangential component, we take the position function r, do its derivative to get v, do the derivative of that to get a, do the dot product divided by the magnitude, and that's all there is to the formula. Very similar, the n comp formula finds v then a, does the cross product, the magnitude of that, and then divides by the magnitude of the velocity. So both formulas are pretty straightforward on the TI-89. Sometimes when we are using those formulas, you can see we get results on the calculator that are in a little different format than what we computed by hand. That doesn't make them incorrect.